Gold and indium oxide nanoparticles support on zirconia, a study of electronic structural and catalytic properties for applications in CO2 hydrogenation. This work is being developed by Thiago Augusto under the supervision of George Piquet and José Maria. Gold catalysts were studied for ethanol dehydrogenation reaction. Now, catalysts gold are stirred in the CO2 hydrogenation reaction under high pressure. The catalysts were modified with indium oxide by impregnation with method in zirconia. The results indicate the metallic nanoparticles hide especially on the surface of the support. When adding indium oxide, change in the area are observed. The TPR profile of bulk indium oxide exhibits a peak center around 650 degrees Celsius, attributable to the characteristic reduction of crystalline indium oxide to in metallic. For the reduction of indium oxide zirconium oxide, the main reduction peak assigned to reduction of crystalline phase indium oxide is shifted to lower temperature at 238 degrees Celsius, indicated of the presence of indium and zirconia interaction, which facilitates the reduction of the support indium oxide. For the catalysts with gold, the TGA under hydrogen atmosphere indicated that only changes below 200 degrees Celsius, which is the reduction temperature of gold. Analysis by 10 for the indium oxide shows the nanoparticles contain internal voids as nanocapsules. The particles are perfectly crystalline and the lattice fringes record corresponded perfectly to indium oxide phase. For the sample indium oxide, zirconium oxide, is interesting to note that all the particles are covered by a thin layer. Interestingly, the indium signal is located at the edge of the zirconium oxide particles, supporting the idea the amorphous shell corresponds to indium oxide. For the sample gold indium zirconium oxide, it is important to highlight that the samples doesn't show the indium oxide amorphous shell around the zirconia particles. Instead, small entities of about 1 and 1.5 nanometers in size are observed of the zirconia particles. Particle size distribution are shown for the samples. The Raman spectra of the samples indicate that preservation of vibrational modes assigned to monoclinic zirconia at lower intensities. The indium load in the sample is less than 7% and justifies the relationship. The intensity of indium oxygen in indium increases with the presence of zirconium, suggesting that more oxygen vacancies are generated. In addition, with the presence of gold, the ratio of intensities for the vibrational modes follows the increased trend up to 0.22% of gold and decrease with increase to 0.84 and 1.61% respectively. As the metallic content of gold increases, lower intensities are observed due to the presence of the nanoparticles covering some oxygen vacancies. The catalytic test in high pressure at 50 bar for samples with 0.22 and 0.84 and 1.61% of gold and the same content of indium around 6.5% indicated that with the increase of gold, the methanol yield at 300 degrees Celsius is reduced. The results indicate that the CO2 conversion and the selectivity for methanol improve with the presence of indium oxide. The oxide favors the catalytic activity. The highly dispersed structure suggests as a major active site to convert CO2 to methanol. Drifts, XPS, and DFT studies are being carried out and will contribute to proposals for the reaction mechanisms involved in the reaction. Thank you.